Let's look at basis, dimension, row space, and column space. For example, can you express any vector in R2, that is two-dimensional space, as a linear combination of 1, 0, 0, 1? Yeah, any. How about 1, 0, 0, 1, and 5, 12? Can you express any vector in R2 as a linear combination of these three? Well, yes, but 5, 12 is unnecessary because 1, 0, and 0, 1 already span R2. In some situations, we're looking for the smallest set of vectors that spans Rn, or a subspace of Rn. We call such a set a basis for Rn, or a basis for that subspace. In the above example, 5, 12 can be expressed as a linear combination of 1, 0, and 0, 1, so it's not needed in the basis. Vectors which can be expressed in terms of other vectors in the basis are not needed in the basis. To make the set as small as possible, we need this set to be linearly independent. Let H be Rn, or a subspace of Rn. A set of vectors is a basis for H if it spans H and it is linearly independent. Every basis of H has the same number of vectors. We call this number the dimension of H and denote it by this symbol here. So any linearly independent set with this many vectors is a basis for H. I desperately need an example here. For example, find a basis for R3. Well, how about 1, 0, 0, 0, 1, 0, and 0, 0, 1? This is the standard basis for R3 because it spans R3. You can express every vector in R3 as a linear combination of these, and it's also a linearly independent set. These are the vectors E1, E2, and E3. So those are usually the names we give to those vectors. Determine if 1, 2, 3, 4, 5, 6, 6, 10, 15 is a basis for R3. Well, R3 is three-dimensional, so any linearly independent set with three vectors is a basis for it. Let's show that this set is linearly independent. The rows of the square matrix A are linearly independent if and only if the determinant of A does not equal 0. So let's again look at, our vectors are 1, 2, 3, 4, 5, 6, 6, 10, 15. So we're going to make those the rows of this matrix. And notice that the determinant of this matrix is -3, which is not 0. So the rows are linearly independent. In other words, this set of three vectors is linearly independent, and thus it's a basis for R3. Determine if 1, 0, 0, 0, 1, 0 is a basis for R3. No, it's not. It doesn't span R3. You'll never get the vector 0, 0, 1 as a linear combination of these two. Not going to do it. Determine if 1, 0, 0, 0, 1, 0, 0, 0, 1, 4, 5, 9 is a basis for R3. Again, same story. It's not linearly independent. You can express 4, 5, 9 as a linear combination of those other three vectors. Find a basis for the solution space of this system of equations. Okay, so what we do is represent this system as an augmented matrix like this. We know how to do this. And then we get it in reduced row echelon form like this. So in other words, we have x1 minus x3 minus 2x4 equals 0, x2 plus 2x3 plus 3x4 equals 0. Now we move these guys to the other side of the equation, these free variables, x3 and x4, and we end up with this. x1 equals x3 plus 2x4, x2 equals negative 2x3 minus 3x4. In other words, x1 is x3 plus 2x4, x2 is negative 2x3 minus 3x4, x3 is just x3, and x4 is just x4. We pull out the x3 and x4, and we can write this vector as x3 times 1, negative 2, 1, 0, plus x4 times 2, negative 3, 0, 1. That means the basis is 1, negative 2, 1, 0, 2, negative 3, 0, 1. These are the canonical solutions to this system of equations. Every solution is a linear combination of these. Find a basis for the null space of A equals 1, 1, 1, 1, 2, 3, 4, 5, 5, 7, 9, 11. Okay, recall what we mean by the null space. It's the set of all vectors x such that AX equals 0. And again, a basis for the null space is going to be 1, negative 2, 1, 0, 2, negative 3, 0, 1. Because as we saw a moment ago, if we're looking at a solution to the system, basically we're trying to solve this system of equations, we saw that every every solution is just going to be a linear combination of these. So that's going to be a basis. Let A be an m by n matrix. The column space of A, which we denote by this symbol, is the set of all linear combinations of the columns of A. It is a subspace of Rm, and that's because A has m rows, and therefore every column has m entries in it. The pivot columns of A form a basis for the column space of A. So notice, the pivot columns of A form a basis for the column space of A. So let's find a basis for the column space of this matrix A. Well, the reduced row echelon form looks like this, and this tells us what the pivot columns are. The first two columns are the pivot columns, because you got the leading one here and the leading one here. Thus, a basis for the column space of A is 1, 2, 5, 1, 3, 7, because we're looking for the pivot columns of the original matrix. Okay? Note that these are the columns of the original matrix A and not the columns of the reduced row echelon form of A. So don't make that mistake. Be careful. Find a basis for the vector space spanned by 1, 2, 5, 1, 3, 7, 1, 4, 9, 1, 5, 11. Let's make them the columns of a matrix and then find a basis for the column space of that matrix. Well, we just did that above. So, we know we made them the columns of a matrix in the previous problem. And so to find a basis for the column space of the matrix, we did that. Okay, the basis is going to be 1, 2, 5, 1, 3, 7. Let A be an m by n matrix. The row space of A, which we denote by this symbol, is the set of all linear combinations of the rows of A, and it's a subspace of Rn. That's because A is a matrix with n columns. And so, if it has n columns, that means that each row has n entries in it. The non-zero rows in a row echelon form of A form a basis for the row space of A. So let's deal with our favorite matrix here. Find a basis for the row space of this matrix A. This is what the reduced row echelon form looks like. This is a row echelon form of A. It's not unique. There are other row echelon forms of A. It's the only reduced row echelon form of A, but there are other row echelon forms. So the non-zero rows are going to form a basis for the row space of A. Thus, the basis for the row space of A is 1, 0, negative 1, negative 2, and 0, 1, 2, 3. The basis for the row space of A is not going to be unique. We used the reduced row echelon form, but really any row echelon form would have been sufficient.